Hello and welcome. Today, we're going to be chemical architects. Our project? To build one of the most fundamental molecules in organic chemistry right from the ground up. So you might want to grab a hard hat, because we're diving into the builder's guide to benzene.
So here's our blueprint for today. We're going to start with the foundation, the benzene building block itself. Then we'll figure out how to name our creation when we add just one piece and then a second piece. After that, we'll see what happens when things get a little more crowded. And finally, we'll look at how to actually put our new molecule to work. It's a nice, logical build, one step at a time.
All right, first things first, let's lay that foundation. Section 1, the benzene building block. You know, every great structure starts with a single, absolutely crucial component. And for us, that's benzene.
So you've probably seen this simple hexagon everywhere in chemistry, right? But what is it, really? Why does this one specific shape show up again and again, forming the backbone for so many different things? Well, at its core, benzene is an aromatic cyclic hydrocarbon. Now, that sounds like a mouthful, but let's break that down real quick. Hydrocarbon, easy. It's just made of hydrogen and carbon. Cyclic just means those atoms are all joined up in a ring. And aromatic? That's kind of the magic word here. It's a key term in chemistry that points to its most important feature, this incredible, almost unexpected stability. These properties really tell us how benzene is going to act out in the real world. So it's nonpolar, meaning it doesn't have positive and negative ends. And because of that, just like oil, it's insoluble in water. You can see it right there in the beaker, they just don't mix. It's also less dense than water. And maybe the most important thing to remember, the entire molecule is planar. It's totally flat, kind of like a tiny little plate.
You know, for a long time, the structure of benzene was a huge puzzle for chemists. Their best guess was what you see here, a hexagon with single and double bonds that just alternated. It made perfect sense on paper, but the problem was, it didn't match how benzene actually behaved in experiments. And this is the solution they came up with. It turns out, those electrons aren't locked into place. Instead, they're delocalized, which is a fancy way of saying they're shared equally among all 6 carbon atoms. Think of it like this. It's less like fixed walls in a house and more like a big, open-plan living space where the electrons can just roam around freely. This is what gives benzene its incredible stability, and it's why we often draw it with that circle inside the hexagon.
Okay, foundation is laid. Time for section 2, the one-piece puzzle. We're going to start building. This is what happens when we add just a single component to our benzene ring, what chemists call a mono-substituted benzene. Naming this first build is wonderfully, refreshingly simple. It's just 2 steps. First, you name the piece you attached. That's the substituent. Then, you just tack on the word benzene at the end. That's it. So if you stick a chlorine on there, you get chlorobenzene. A nitro group, you get nitrobenzene. It's really that straightforward. All right, let's level up. Now for our 2-piece puzzle. This is where we add a second component, and when you attach 2 groups to the ring, creating a dis-substituted benzene, suddenly where they are in relation to each other matters a lot. See, with a second piece added, there are only 3 possible places it can go relative to the first one. It can be right next door, it can be 1 spot away, or it can be directly across the ring. These different arrangements are called isomers. Same parts, just put together differently. And because they are different, we need a naming system that can tell them apart. So to handle this, chemists basically have 2 systems. On one hand, you've got the official universal standard from IUPAC. It uses numbers to pinpoint exactly where everything is. It's super precise, no confusion. Then you have the classic shorthand, which uses the prefixes ortho, meta, and para. You can kind of think of this as the common nickname system. Let's see what those nicknames actually mean. First up is ortho, or just O for short. This is what we call it when the 2 substituents are direct neighbors on the ring, sitting right next to each other. We call those positions 1 and 2. Now, if we move that second piece over 1 more spot, we get the meta arrangement, or M. Here, the 2 groups are separated by 1 empty carbon atom, putting them at positions 1 and 3. So they've got a little bit of breathing room between them. And the third and final possibility is para, or P. Honestly, this is the easiest one to spot. The 2 groups are directly opposite each other, right across the ring, in what we call the 1 and 4 positions. They're as far apart as they can possibly get. So you have ortho, meta, and para, next door, 1 spot away, and directly across. So what happens when our build gets even more complex? What if we add more than 2 pieces? Well, that brings us to section 4, polysubstituted benzene. But don't worry, the logic we've just learned still holds up.
Okay, so the crucial rule here is that once you have more than two groups, that ortho-meta-para shorthand, it just doesn't work anymore. We have to fall back on that clear, precise IUPAC numbering system. And the goal is always the same. You number the carbons on the ring to give all the attached groups the lowest possible combination of numbers. It's all about being systematic so everyone's on the same page.
We've laid our foundation, we've learned how to name our structures, now for the final section. And honestly, this is the most exciting part. Putting benzene to work. This is where we see how chemists can actually tweak this stable ring to build totally new and useful molecules.
Think of this list as benzene's core chemical toolkit. These are the go-to reactions that chemists use to add different groups onto the ring, and each one unlocks totally new properties. Like halogenation adds things like chlorine or bromine, often a first step in making pharmaceuticals. Nitration adds a nitro group, which is crucial for making explosives like TNT, but also for making dyes. Every reaction you see here is a fundamental tool for transforming simple benzene into something much more complex and valuable.
And that, right there, is the real power of this molecule. It's not just some abstract hexagon on a page. It is the foundational block for this incredible range of materials that shape our world. We're talking everything from life-saving medicines to modern plastics to advanced electronics, which really makes you wonder, with a building block this fundamental and this versatile, what on earth are we going to build with it next?